Hello, this is Jeremy Singer from the University of Glasgow in Scotland. I want to talk to you about parallel programming in Python. Python programmers have GPUs too. I want to start with a big shout out to Degis Jacob. He's my PhD student at the University of Glasgow. Degis has almost finished his thesis. His deadline is the end of July, so he's only got 3 weeks left to go. He's busy writing and I'm busy commenting and correcting. But the basis of his thesis is really the work that I'm presenting today. So I want to start by highlighting two trends. Firstly, the popularity of the Python programming language. You have a look at any programming language chart you like, and Python is really growing in popularity. So here's one. This is, I think, the TOB chart. Here's another one from IEEE Spectrum. That's put Python right at the top. And this is another chart here. Again, Python's certainly in the top 5. Recent article from The Economist. Python has brought computer programming to a vast new audience. And if we look at programming languages that are used in university level CS 101 courses, we find that Python is, again, one of the most popular languages that's used to teach students about coding. And apparently there are more Google searches for Python than for any other language. So that's the first trend. Python is a popular general-purpose programming language. Here's the second trend. It's the mass availability of compute accelerators. Things like GPUs, or more exotic accelerators. This is the pink board, which features an FPGA that is programmable from a Python API. You don't even need to buy an expensive FPGA board now. You can rent one from Amazon Web Services. And here's the Google TPU, which again is becoming more readily available for deep learning applications. So, accelerators are commodity items these days. Right, so we've looked at how Python is popular and how accelerators are available. Now, sadly, we want to think about how Python is slow. So there's a website, I'm sure you've seen it, it's called Computer Language Benchmarks Game, and it encourages people to submit code that implements various algorithms in different programming languages. These are all fairly well-known, straightforward algorithms. For instance, there's the n-body planetary gravitational problem. Then there's computation of a Mandelbrot set. And the source code is written in various languages, but the underlying algorithms are equivalent. So we see that for the particular n-body problem that's specified for the Computer Language Benchmarks game, a C program takes 7 seconds. A Python program takes 2 orders of magnitude more, nearly 800 seconds. For Mandelbrot, a C program takes 2 seconds, and again, 2 orders of magnitude more. Python programs taking 260 seconds there. Python's not just inefficient in terms of time, but also in terms of memory, as we note here. So if we're interested in higher performance Python code, how can we go about achieving that? Why is Python so slow? Well, let's ask Google. And it tells us straight away, Python is slow because of the global interpreter lock. There's a feature in the Python interpreter, interpretation slow anyway, but the global interpreter lock means you can't do multiple things concurrently. So there really is a built-in prevention of parallelism into the design of the Python ecosystem. There are various approaches to improve Python performance. Some of these include just-in-time code generation. So, for instance, the PyPy runtime for Python is a tracing JIT compiler, which is much quicker than the CPython interpreter. Also, a recent development is the number code generator, and this is particularly useful for scientific code that uses NumPy data types and corresponding libraries, and this allows us to generate very efficient CPU machine code, perhaps sometimes vectorized machine code for compute-intensive type loops in Python. They have to be written in a certain restrictive way in order for number to be able to get the high performance out. Indeed, there are number backends as well for GPUs like CUDA and so on. But really what you're doing is you're writing very restrictive high-level Python code that can be mapped on a one-to-one basis to a CUDA kernel. What we see here is that performance is effectively equivalent to the amount of parallelism you can extract from your code, as Moore's law would tell us these days. And I suppose in the default Python environment, parallelism is problematic because of this global interpreter lock that prevents you from doing things in parallel in the standard Python ecosystem. But here's a question: is Python a good candidate for parallelization? Well, if we have a look at some basic Python code, the stuff that end-user developers might write, we see these kinds of features. Lots of simple for loop constructs, which have limits specified by explicit range functions. One of the features of the Python for loop semantics is that you can't really update iterator variables to skip iterations in the same way that you would in C-like languages. Again, it's not possible to alias the iterator variable in Python. And I suppose if we're looking to speed something up, it's good to start with something that has a low baseline performance, and that's certainly true for interpretive Python code. There are some difficulties though. We know that Python is a dynamic language, so types aren't generally known, resolved until runtime. And indeed, data structure shapes and loop bound values aren't known until runtime in many cases. In recent times, one of the most popular programming environments for Python has become Jupyter notebooks. These interactive web-based computational notebooks are being used by all manner of end-user developers, from data scientists to beginner coders to zoologists to archaeologists. We notice a paper in 2018 called Exploration and Explanation in Computational Notebooks, which downloads over 1 million notebooks from GitHub and analyzes these notebooks to see what kind of code they contain. When we looked at a sample of these notebooks, we found that many of them did have some number of simple for loops in them. And indeed, of the notebooks that had for loops, we found that many of them had very low levels of nesting, very shallow nested loops. So we see from a sample of end-user code that the control flow constructs they use are definitely amenable to parallelization. So our approach is a classic loop dependence analysis. We're targeting affine loop nests. We do the standard kind of ziv, siv, miv dependence tests. And really this is, stuff that's been done since the 1970s, 1980s on Fortran code. Optimizing compilers for modern architectures has all these details in its textbook. As we look at loop nests in plain old Python, we're looking for true dependencies, anti-dependencies, and output dependencies. All these things influence the serializability of the code and mean that it can't necessarily be executed in parallel. So there are some specific novelties in our approach in the ALPyNA system, and I guess the main novelty is that our analysis is staged. It's split over two phases. There is an ahead of time analysis, when we first see the code. This is like a kind of static analysis as soon as the Python source text is introduced to the runtime. At this stage, we look at the code and build loop nest data structures to model the shape of the code and try to resolve as many loop bounds as we can. And then we look for dependent relationships between the variables that are mentioned inside the loop bodies. The second stage is just-in-time analysis, and this is when the loop is about to be executed, and we do some Python introspection, some dynamic analysis to try and identify the types of the variables, particularly the NumPy arrays that are being accessed inside the loops, and also, of course, the loop bounds themselves, which by now should be resolved to constant values. This is an overview of the ALPyNA architecture. This is our system here. So on the left-hand side, what we see is the static machinery here. And we notice that we start off with some Python code, which is parsed, and we do some kind of dependence analysis. And where possible, we do some parallelization and generate kernels. Okay, but it might be the case that we can't necessarily analyze everything statically, and so we defer a lot of analysis until runtime. Here on the right hand side we've got the runtime analysis, and here we do more dependence analysis and parallelization, and eventually we'll do JIT compilation via the number system and execute our code. So the ALPyNA framework has some internal data structures, particularly the loop landmark structure. This is our representation of the loop nesting structure in the code from which we can do our dependence analysis. The dependence map is our way of representing dependencies between the different variables and data structures. And then we also have these CUDA kernels generated with holes in them for perhaps loop bounds or data types that we need to fill in later. So as I say, the analysis is staged. It's all done in Python using standard libraries. So what this means is, although at the moment we're embedded inside the C Python runtime, the default Python VM, it could be extended to other systems, like for instance Jupyter's IPython notebook framework or the PyPy just-in-time compiler. And then each code variant for the loop nest is embedded in a separate namespace, which means we can switch between or select adaptively whether we want to execute the original interpretive code or the just-in-time compiled code, which might have been parallelized for the GPU. Okay, so let's talk about the two different hardware platforms that we use to evaluate our performance. M1 is a server class architecture, an 8-core CPU with a pretty beefy GPU. M2 is more of a desktop class machine, a quad-core Intel i7 and by now a particularly outdated NVIDIA GeForce graphics card. We're going to use, as I've already said, plain old Python programs with just standard loops in them in order to do our benchmarking. We select 12 benchmarks from the BLAST routines in the polybench suite, some from the Computer Languages Benchmarks game, which I mentioned before, and some from the Number Benchmarks suite as well. There are 12 benchmarks in total. Here they are here, and in this table we characterize these benchmarks based on their loops and the number of statements inside the loop nest. You'll notice that some of the benchmarks like Black-Scholes and Mandelbrot have perhaps more complexity inside the loop bodies than others do. And where you see there are multiple loops, these are all possible candidates for parallelization. This is more of an irregular loop nest, an imperfect loop nest, rather than the perfect loop nests of the other benchmarks. I'm just going to show you some of the results on the M1 server class machine here. These were sampled, but there are plenty more results as well. So there are 3 bars for each input size. The input sizes here on the x-axis. Okay, so this is a one-dimensional array here for Black-Scholes, where the size is increasing exponentially on x. And what you see on the y-axis, the time, this is in seconds. These are actually log-scale graphs on y. So we're reporting 3 execution times for each input size for each benchmark. And the 3 execution times in red, yellow, and green are as follows. The virtual machine execution time is just the default Python interpreter that's running. The CPU execution time here is the execution time with code that's JIT compiled by number but not parallelized. And then the GPU execution time on the right here is the time taken by the code when it is JIT compiled into CUDA code, parallel CUDA code, and then executed on the GPU. And I just picked these 4 benchmarks here, but they do show us the significant differences between the benchmarks. So you'll see that the red time here for the VM starts off the smallest. This is for the tiniest benchmarks here, okay, but then increases rapidly. And in fact, we don't report the red interpreter-only results for the largest input sizes because we time out after 2 hours of interpretive execution time for these largest benchmarks here. We'll notice that as the input size increases, for the Black-Scholes benchmark, for instance, we'll see that the CPU time increases, but not as rapidly as the VM time, and so the CPU time is at larger input sizes, much quicker than the VM time. Then the GPU time, sorry, I've changed slides there. The GPU time here we can see is, well, increasing again slightly, but there's generally an overhead, particularly for the smaller input sizes of the GPU. This is because of the cost of data transfer and also the kernel compilation time, which is part of the runtime overhead. In some benchmarks, like this one here, this is filter bank correlation, this benchmark here, we see that the VM time is never reported because it's always so large. We always time out after 2 hours for the VM. But for the GPU, we notice that the time is always much smaller than for CPU. Just to show you the overhead of the analyses, so these are included in the overall execution times, but we see that some kind of ahead of time analysis that takes place for CPU and GPU execution, then the compilation of the kernel or the number code itself. This is always particularly small in relation to the overall execution time of the benchmarks, particularly at the larger input sizes. So there are full details in 2 published papers from Array 2019 and the Dynamic Languages Symposium 2019.
as well. What we found was that in the best case for larger input sizes, the CPU executes hundreds of times faster than the interpreter. The GPU, in some benchmarks, executes thousands of times faster than the interpreter. But what we notice is that for smaller input sizes, actually the interpreter wins because it doesn't have to pay any compilation overhead or data transfer overhead for CPU to GPU memory transfer. So you see, we need to create a runtime cost model. Given the disparity in performance between the interpreter, the CPU and the GPU execution times for the differing benchmarks and input sizes, we want to be able to select the best back-end target for a particular loop nest with a particular iteration size. We're going to use an analytic cost model rather than a machine learning approach. So our cost model design is going to give us ahead of time estimates for the cost of executing code on a particular back-end device. Just to give you a kind of broad brush sketch of the analytic cost model. So we see here that the cost of interpreting a statement S is the cost of interpreting that single statement S once, multiplied by the product of all the loop iterations for that statement. So F is a for loop, F ranges over all the dominating loop headers of the statement S, and L of F gives us the ranges of the for loops. So effectively we get the product here, which is going to be the iteration domain of the statement. So this gives us the cost of executing that statement. And then the time for executing the whole of the for loop, F, is the cost of interpreting every single statement that is enclosed by the for loop, F. Here's a more complicated model, and this is telling us here about the cost of interpreting code on a GPU. So this is for a statement S, and what we find is there's again the product of loop iterations. LF is going to give us loop bounds again. Some of these iterations can't be executed in parallel. Some of them can be executed in parallel, and for the ones that can be executed in parallel, then what we find is we have this factor here, which reduces the execution time because of the parallelism. Okay, and then the cost model goes on to consider the relative cost with which the GPU can be supplied with data and code by the interpreter. So that's just a quick overview of the cost model. But when we plug in the full analytic cost model into our system, what we find is that it can tell us with remarkably good accuracy whether our CPU code or GPU code is going to be fastest. And we see here that the faster code is a logarithmic y scale. The faster code is initially executed on the CPU, then there's a crossover point, and above a certain input size, the faster code is executed on the GPU. And just for this short interpolated range here, we see that the cost model mispredicts whether the CPU is faster than the GPU. In some cases, like here, for this benchmark SAXP, the CPU is always faster. For larger iterations, domain sizes rather, the predictive cost model predicts that the GPU will be faster. In fact, it's still slightly slower. But overall, our 12 benchmarks, the performance penalty relative to an Oracle predictor is only 14%. So our cost model generally gives us very good accuracy for predicting the best backend to execute our code. Okay, let's quickly consider future work for this system here. We want perhaps an enhanced cost model to select dynamically the best performing backend. At the moment we can select between CPU and GPU. We also want to consider the interpreter because for very small input sizes, the interpreter is actually quicker than the overhead of doing the compilation and running the code on a CPU or GPU. We might also consider alternative backend targets such as FPGAs or multi-GPU setups. And also we want to think about GPU kernel fusion, so possibly fusing together multiple loop nests rather than executing them one after another and transferring the data back and forth from the CPU to the GPU. Just a note about related work, alternative approaches to harnessing parallelism in Python. And we split this into 4 different kinds of parallelism. Library level parallelism is where the Python code is executed sequentially but calls out to particular domain specific libraries like the scikit-learn library for machine learning or the OpenCV library for image processing. And these, although they have Python APIs, generally bind down to low-level C or C++ code, which is often vectorized or perhaps sometimes executed using OpenMP or even OpenCL. So there is parallelism inside the libraries. Second approach is embedded domain-specific languages to do GPU offload, and PyCUDA and PyOpenCL are very simple ways of generating kernels for Python code, but they require you to write very low-level GPU code as strings in your Python and then compile those for the kernel on the fly. There are alternative approaches like the LoopI approach, which again expresses parallel loops in a rather esoteric notation. A more high-level approach might be to use task graphs for high-level workflows, and this is particularly the approach that's used in the TensorFlow system. Pattern-based parallelism is also popular, so particular code stereotypes like maps, and reducers and filters, which are effectively embarrassingly parallel on large-scale data structures, can be parallelized again implicitly in your Python code.
So, in conclusion, our ALPyNA system is for end-user parallelization. We're working with standard Python loops, and we don't require any invasive user annotations or extra analysis or verification. It's plain old Python code that's being parallelized. And in this way, we improve the productivity of everyday software developers. We make the performance portable in that we're relying on tools underneath like Number and tuning frameworks. And we use state-of-the-art dependence analysis in this novel staged manner with its cost model to drive it. So there we have it. Python programmers have GPUs too, and now they can use them nice and easy.
Now, just a quick advert before I go. Along with a colleague, Wim van der Bouwde, I wrote a textbook on operating systems, particularly focused on Linux for the Raspberry Pi. We wrote this last year. This is a textbook suitable for undergraduate level operating systems courses. Very hands-on, very practical, as you'd expect with the Raspberry Pi focus. And it's published by ARM Education Media. Do check it out. You can get in touch with ARM to get an evaluation copy, and hopefully you'll be able to recommend it to all your students. That's the end of the commercial break. Thanks everybody.